All right, this video is about inducing an EMF in a moving conductor. Now, the picture is going to take a little explanation, so just so that we understand exactly what's going on. Okay, all the little circles with the dots in it are indicating that we're putting something in a magnetic field that is sticking out of the paper. Okay, so coming right towards you. And then I have a wire, a U-shaped wire. Okay, and then we put a conductor on top of the wire. So this is like a little sliding bar, if you will. So like a piece of metal that goes from one side to the other. Now, what happens here is this bar, if it's touching the wire, creates a loop that would have a certain area. Okay, if we slide this bar over, and that's where I have my little dashed lines here, I've now made a larger area. Matter of fact, we've had a change in the area. Okay. Now, in order to induce the EMF, you need a change in magnetic flux, which means the area has to go up. Well, this particular conductor will have moved from here to here. That's a change in position. A change in position is equal to a velocity times a change in time. So if I really want to figure out here, well, what is the change in area? Okay, well, whatever the length is of this conductor, that represents one dimension of the area that's going to increase, multiplied by the displacement, the delta x. So the length of the conductor multiplied by the displacement of the conductor, that would give us our change in area. But we've also written that the delta x could be a v delta t. So the change in the area is really the length times the velocity times the change in time. So if I think about this, if this is what my change in area is, if I go down into Faraday's law here, that's got the EMF is the change in the flux divided by the change in time. Okay, let's put a little, got the negative sign in there. Okay, then in this particular case, if I write, instead of change in flux here, I write B delta A, okay, divided by delta T. I can replace delta A with L V delta T, and you're going to see that there's a delta T there and a delta T there, so those would go away. And the induced EMF in a moving conductor is equal to the field times the length of the conductor times the velocity of that conductor. And all of those things need to be perpendicular, which they are. The length here is perpendicular to its velocity, and the field is coming out of the page. Those are all at 90 degrees from each other. Oftentimes, this EMF is called motional EMF. Now let's also talk about, okay, the direction of the current. Well, if the flux is getting larger, meaning there's more flux coming out of the page, then the wire is going to create a magnetic field in response to that that would be into the page. And if you use your curl rule, okay, into the page, my fingers go into the page, you're going to notice that my thumb is on the bottom here and would curl around to the top and across. Therefore, the current created in the wire is clockwise. Now you might be saying, well, why is this relevant? Okay, well, an airplane is an example of a conductor that flies through the Earth's magnetic field. However, there's really no path for the electrons to leave. So what you do is you simply build up a voltage on the plane. So the plane actually builds up a potential on it. Now, luckily, it's a very, very small amount, so it's not dangerous at all. But an airplane will build up an actual voltage as it flies through the air.